California Baptist University. This is my presentation. So let's start with some fun facts about rabbits. To begin, they are quite various. So they do have 300 breeds across the globe. 14 million of those are domesticated rabbits, and they're used as pets, which is crazy because there's 14 million rabbits used as pets, then how many are there in the wild? Then we're talking about the gestation. So the gestational period for a rabbit is typically between 27 to 33 days, but it can vary slightly lower, or upwards towards the 40s. Now let's talk about the offspring. So female rabbits can have anywhere from 1 to 14 babies per pregnancy, which does make them ideal candidates for testing because they do multiply fast, so you do have a lot of product to use when testing. And that also plays into the lifespan. The lifespan for rabbits in the wild typically is only from 1 to 2 days, but domesticated, more pampered rabbits can live upwards from 10 to 12 years. And so wild rabbits are typically used for testing sometimes because of their short lifespan. It's a big number. So 184 billion, 597 million, 433,860 rabbits can be produced from one single female rabbit's offspring in just 7 years. So if you multiply that by that number, that will give you a good estimate of how many rabbits are here in the world. So now let's begin talking about fertilization, a match made in bunny heaven. Here's some essentials for the fertilization. First of all, we have mammalian. So the fertilization of rabbits is a mammalian fertilization. Rabbits are mammals, so I would assume so. And so rabbit development does follow the guidelines of all mammalian fertilization, including specific parts that do appear in mammalian fertilization rather than aquatic animals. And so now let's move on to internal. So the fertilization of rabbits is internal, does not happen externally in any type of water or anything else like that because they're not aquatic, they are mammals. So they do reproduce internally, and all of the development until birth happens internally. The sperm also goes through capacitation. The embryo does also go through capacitation as well. Capacitation of the sperm basically makes it fertilize the egg better. So it makes it go faster. It gives it a drive like none other, that will help this happen, the meet cute, mom met dad. Here is a visualization of fertilization. Here you can see an oocyte with sperm here. 3 sperm do approach it, but 2 of which fall off due to toxicity in the vaginal canal and uterus. And only 1 of the sperm does survive enough to actually fertilize the oocyte. So here, only 1 sperm goes in, and within that split second of it going in, bam, slow block and fast block to prevent polyspermy from happening. So let's talk about some accountable activity. So the first cleavage furrow is basically the first time that the fertilized egg divides. And so the first time it divides, it results in the 2-cell stage because 1 cell going into 2 does result in 2 cells. This does happen between 16 to 22 hours after fertilization happens. Then we have the second cleavage furrow, which happens 1 to 1.5 days after conception. This results in the 4-cell stage, since 2 times 2 is 4, I would assume so. Then we have the third cleavage furrow, which happens 1.5 days into conception, as I talked about from the second cleavage furrow. This one does result in the 8-cell stage because 4 times 2 is 8. I would assume so that as well. And then we have the fourth cleavage furrow, which basically happens in the marilla stage. This stage is called the marilla stage, but I will talk about that in just a moment. This does happen between 1.5 to 3 days after conception and is also resulting in the 16-cell stage, since 8 times 2 is 16. So here's the marilla stage. The 16-cell stage that happens around 3 days after conception. It's basically a solidified mass of blastomeres happening through capacitation, which creates tight junctions, which give the embryo its round shape. The embryo will then develop stage by stage until it reaches the upper part of the uterus, and then it will reach the marilla stage by the time it reaches that part of the uterus as well to prepare for implantation. So then the blastocell appears after the marilla stage. At this point, the embryo does create a small opening in its membrane, which will allow for fluid from the uterine cavity to go into the cell. At that point, it does rapidly start expanding, which will increase its absorption of the fluid from the uterine cavity. This fluid does go through the zona pellucida and the morula, so there is a type of opening there. It's also capable of all things, which means that it's pluripotent, such as giving rise to the intracellular mass or the trophoectoderm, which I'll talk about in just a moment. So this is the first decision in a rabbit's life. Is it embryonic or extra-embryonic? This is the question that the tissue will go through. So let's talk about trophoblasts. So trophoblasts do come from those 16 cells. So either those 16 cells will basically develop in very certain ways once they get to that stage. Once they get to that stage, smaller ones do tend to go through the trophoblast side, and then the larger ones will go through the intracellular mass. So trophoblasts are smaller, flatter cells that do line the embryo at that point. It does create a layer between the morula, which will help bring nutrients into the embryo at a later stage. It also acts as a placenta and helps with oxygen intake and nutrient intake like that. It also will give rise to the chorion, which is the section of the placenta which gives nutrients to the embryo. So the intracellular mass, also called the ICM, will give rise to every tissue type in the body except for trophoblasts. So before the morula stage, we have 16 cells that are capable of anything in the entire body. Those 16 cells do contain the entire human genome. But at the point of deciphering whether or not it will be an ICM cell or a TE cell, TE is going to be our trophoectoderm, it will go through that kind of decision-making process of deciphering which cells will go here and which cells will go there. At that point, then we do have the intracellular mass, which is not able to create the trophoblasts. Once we have those 16 cells, once they go through either trophoectoderm or intracellular mast cells, they will not be able to go back. So trophoectoderm cannot produce intracellular mast cells, and intracellular mast cells cannot produce the trophoectoderm. So once those cells pass that stage, ICM will be the only type of cells that will be able to produce every type of cell in the entire body. So let's elaborate more on that. So the decision to become either an ICM, the intracellular mast cells, or the trophoectoderm is quite interesting. It involves a lot of important parts, one of which is the symmetry of the cleavages. As we've talked about cleavages 1 through 4, the way that they create their furrows, which is the way that the one cell becomes two, these two parts right here, these will be the furrows. And so cleavage furrows, and so the symmetry in that does have a big part to play on whether or not that cell will become a trophoectoderm cell or an ICM cell. And we'll talk about that more later. I do have a visualization of that. Then also OCT4. OCT4 is a transcription factor, octamer binding transcription factor 4. This does prevent ICM cells from becoming trophoectoderm cells or giving rise to those type of cells. It basically holds it in its place, and CDX2, which is cotyl-related homeobox 2 transcription factor, is a transcription factor that's essential for the trophoectoderm to become the trophoectoderm. Without this transcription factor, trophoectoderm cells will become intracellular mass, which will basically just give rise to just a big ball of ectoderm and endoderm, which won't give rise to anything. So this is very important that these transcription factors are present to prevent one from becoming the other. So here we talk about the symmetry of the cleavage. So here we have one cell, which is going through cytokinesis, coming one from two. And so here it is symmetrical, so it's going straight through the middle. This creates two external cells, as this is the membrane of the embryo. And then asymmetrically, if it happens straight through the middle, then it'll create one external and one internal. And the internal will become the ICM. Here is a visualization of the blastula. So the blastula is basically an embryo that has a cavity in the middle called the blastocells. Here we see the ICM, which has stuck to one side of the embryo, and then here we see the trophoectoderm, as well as the morula, and last but not least, the zona pellucida. So let's talk a little bit more about that zona pellucida. So the zona pellucida basically encapsulates that mammalian vastula for the first few days of the development, but then after time, once the blasteocell starts to absorb that uterine fluid from that uterine cavity, the zona pellucida does thin out to the point of breaking. Visualized by this lovely balloon photo I found by the slow-mo guys. Once this happens, the trophoblastoderm is then exposed to the uterine lining, which is called the marusca. And once that part is exposed, it's able to release villi, which will then penetrate the marusca and then be able to finish implantation. So implantation, the warm welcome, happens about 5 days into rabbit gestation. An overview of this, firstly, the trophoblast will release that villi that will grow into the marusca, embedding it into the uterine lining and completing implantation. The endometrium of the uterine lining encapsulates the embryo, which I'll visualize in a moment, meaning that the embryo will not grow freely into the uterine cavity, but will grow into the uterus itself. The embryo will then continue to develop inside of the uterine lining, and blasticinin does appear and is secreted to preserve the embryo itself, and will also regulate nourishment as well. Make sure it's not undernourished or overnourished. So here's a visualization of that happening as well. So here's going to be the marusca, which is that outermost lining of the uterus, as well as the endometrium, and then this is going to be our uterine cavity here. Here's our mammalia blastula coming in at the side with its villi embedding itself into the marusca. Then this marusca cell will then, the marusca lining will then embed itself over that mammalian blastula, encapsulating it into the uterine lining, and then here you'll see that that will grow inside of the uterus. Now we talk about gastrulation, the spring cleaning of the cell that happens around 6 days. So let's talk about a little preface about this. So gastrulation does include migration, renaming, and flattening. These are some very important parts of gastrulation. So the migration of the cells on the lower part of the embryonal knob, facing the blasteocell, which is that cavity inside of that mammalian blastula that's empty. Those will migrate, which will create a new layer called the mesoderm. We'll talk about that, called the endoderm. That endoderm will protect that ICM from the blasteocell. It also goes through the renaming because the embryo now has multiple layers. It's not called a blastula anymore, it's called a gastrula, now that we are in gastrulation. It also has to do with the flattening of the cells. The remainder of the embryonal knob, it will basically transform into an embryonic disc, and this will give rise to several different tissue types, including the primitive streak that we'll talk about a little bit later. The second decision of a rabbit's life. The ICM will now make another choice of a lifetime, whether or not to become a primitive endoderm cell or part of the epiblasts. So primitive endoderm, also known as hypoblasts, are cells that are derived from the primitive endoderm, also known as hypoblasts, are cells that are major components of the development of the yolk sac, and they are also extra embryonic tissue. The epiblasts are cells that eventually will develop into the ectoderm, which eventually give rise to the epidermis and nerve tissues in the embryo itself as it develops. These are also internal embryonic tissues, not extra embryonic. Let's dive a little bit more into that. So, the decision to become either an epiblast cell or part of the primitive endoderm is pretty important, and so it also includes a lot of pathways. So this ERK pathway, it blocks and suppresses the primitive endoderm specification while it specifies the identity of the epiblasts. So this pathway does basically inhibit that primitive endoderm from sparking up in those cells and instead promoting the epiblast formation. GATA6 is a transcription factor which is necessary for specification for the primitive endoderm cells, while the ERK pathway suppresses it. It does not suppress NANOG, which is a transcription factor which is necessary for the specification of the epiblast, not the primitive ectoderm. And so while this GATA6 is helping out that primitive ectoderm, helping that promote and start growing, NANOG is then going to promote the other epiblast. And so while this ERK is suppressing it, this GATA is going to start helping that primitive endoderm decide its fate and start growing. And then FGF signaling, which is our fibroblast growth factor. Those levels of the signals will also help because cells that have a higher level of that fibroblast growth factor signaling will tend to go as the primitive endoderm. Those cells will definitely specify that. let's talk a little bit more about that primitive streak. So the primitive streak forms very interestingly. So that embryonal disc will give rise to that primitive streak. It does happen on the posterior end of the embryo, and the positioning of it is that it will basically be limited to that posterior end. It will not go into that anterior end until further when it goes to the that other part. I'm sorry, your other part. Let's go back. So the primitive streak formation. So let's talk about a little bit of positioning and migration. So for the positioning, the primitive streak does occur forming in the posterior end of the embryo at this point, and it's also limited to that area. It won't migrate at all until it's time for the migration portion, which the primitive streak will basically migrate and either give rise to more hyperblast cells or an epiblast layer. It's pretty interesting. So the primitive streak, when they do migrate, it will migrate anteriorly and downward. So basically, some of these cells, as it's migrating and trying to get to the center of that embryo, these cells will basically break off, and they're loose cells that will give rise to other tissues, such as the notochord, which is essential for the embryo development, or those loose cells will join the hypoblasts in creating the mesoderm, which is absolutely essential part of our germ layers. So the mesoderm does give rise to a ton of essential systems, such as the excretory system, the muscular system, the skeletal system, as well as the reproductive system, the cardiovascular system, and the lymphatic system. And then this is also migrating mayhem, because these cells are migrating and they're not sure where to go. Some of them go to the notochord, some of them go to the endoderm, some of them go to the mesoderm. It's kind of confusing. But so the notochord. So we do have the endoderm, which some of these cells will join the primitive endoderm, and they'll give rise to that endoderm formation. And then the mesoderm, which I've already talked about, will basically give rise to all those different systems in the body, and without that, development can't continue properly. Here's a visualization of that. Right here, we're here at that primitive streak right there, which is definitely limited to that posterior end of the cell. And then it will give rise to more portions of that we'll talk about in just a moment. So here's a visualization of the gastrula once it's done. So here we see the blasteocell, which has all those cells around it, with that hollow inside, which will help gather that uterine fluid in from the uterine cavity. Then we have the blastula, which is a little bit more developed, but not quite a gastrula, meaning that the blastula has one layer and the gastrula has multiple layers, such as the ectoderm, the endoderm, and the mesoderm. Also has the blasteocell still in that center. And then here's another one talking about that primitive streak. So here, that orange, that's gonna be the primitive streak right there. So start here in that posterior end, but also migrate towards that center to help promote that other layer that comes from that. So that primitive streak will definitely be migrating, and then those cells will give rise to those other portions. And here we see this rabbit in the center. As you can tell, it's a bit larger than the mouse. Rabbits tend to be larger than mice. But that primitive streak is seen here in the middle. We also have a visualization of this part right here, which does show the embryonic endoderm right here, the extra embryonic endoderm, which happens a little bit farther out, the yolk cells, which happen in this region, as well as the epiblasts, which happen right near the side of the primitive streak where the head process happens, as well as the extra embryonic epiblasts that happen a little bit farther from those regular epiblasts. Here are actual visualizations of what's happening in the rabbit itself. So here's where we left off, right about up here near 14, which is where that primitive streak is growing. And up from there, it will only get larger and more tissue types will only grow from there. So once we start from those three germ layers, the mesoderm, the ectoderm, and the endoderm, all of these layers and all of these different things will happen from those, resulting in a full-grown rabbit, which is ready to be birthed. And this is what it looks like in the end. A really cute bunny, and I'm just really glad that I chose this. Not only because bunnies are cute, but because I used to have bunnies when I was younger. Here's a photo of me when I was about 3 years old with my buddy Snowflake. I had a couple of bunnies when I was younger. All of them were named after princesses. I had Aurora, Snowflake, Cinderella, several. But Snowflake was definitely my favorite, not just because he was super cute, but because he has a mustache. I mean, how could you not like him? He's adorable. And that concludes my presentation on rabbit development. Thank you. And here are my references.